The key graph in all of these are the ones in the top left-hand corner in A. We call this the parent graph, because all of the other graphs that you do after that all have that same shape. They're all related to the one that we started with. And so we did our table of values. You might have done a couple of negative numbers and a couple of positive numbers, and you plug them in, and you cube them, and we get the following points. Now, the shape of the cubic graph flattens out at 0 and then goes up again. Whenever we're drawing our graphs, if a graph continues on forever, we need to show arrowheads. So the first thing I want you to check on yours, did you have arrowheads on the end of your graph? And the key points, if we would label them on our graph, are 1, 1, 0, 0, and -1, -1. Those are 3 key points for your x cubed graph. We could also label 2, 8, and sometimes you might want to use that point because it works out nicer values than 1, 1, or -1, -1. But that is our key graph for the x cubed graph. Now, what we wanted to start to notice is when and how do things move? Because this whole assignment was whichever graph you started with, it got moved to the left or to the right or up or down. And one of our goals is, after looking at all 4 of them, is to start to see a pattern. What makes it move to the left? What makes it move to the right? How can we tell without actually doing a table of values again, without plugging things in? So if we go to the back side of the x cubed graph, for x cubed plus 1, well, that would take your original graph, which is here, and what would the plus 1 do? It moved it up 1. And so you had all the same points, all moved up 1. So instead of having 0, 0, your y value became 0, 1. Instead of having 1, 1, it's now at 1, 2. And instead of having -1, -1, it moved up 1 to -1, 0. In the second one here, there's my original graph right there. And I have an x minus 3. Which way did that one move? 1, 2, 3 to the right. Exactly the same shape that we had before, but the minus 3 moved it 3 to the right. This is the first one where, if you were asked before you started, if I told you x minus 3 moves left or moves right, most of you would have said -3, move left. Because if you see a negative sign and you're thinking about moving right or left, your gut probably would have told you to move to the left. But in reality, what happens is it moves to the right. That's opposite of the first one, right? The plus 1, if I told you it's going to either move up or down, the plus 1, your gut would say, yeah, it's going to move up, and you're right. But the -3 moves it in the opposite direction of what you probably think. The reason for that is, if you think of this point that was at 0, 0, your y value is at 0, what x value would keep it at 0? Would it be a -3 or a +3 to make it equal to 0? It would be a +3 to get 3 minus 3 cubed would still be 0. So anything that's inside the brackets, when I'm going to be talking about language of stuff inside of a function and outside of a function, the plus 1, I would say, is outside of the function because it happens after the x cubed, outside of it. whereas that minus 3 happens inside of the function because it's inside brackets and it's getting cubed as well. Anything that happens inside of the function moves it left and right. Anything that happens outside of the function moves it up and down. And anything that happens inside of the function goes in the opposite direction of what the sign inside. You have x minus 3, you're going to move 3 to the right. If you had x plus 3, like we do in this next one, you're going to move 3 to the left. So here we have x plus 3. That moves it 1, 2, 3 to the left. And then the minus 1 moves it 1 down. Again, same shape that we had before. But if I label what happens to 0, 0, it moved 3 to the left and 1 down. You've seen something similar to this before, but I'm not going to tell you yet what it was. But if you remember, that's great. Because again, in mathematics, one of the things when you're learning something new, if you can make a connection to something you've learned before, that'll make your learning stronger. So I'm not going to tell you what connection I wanted you to make yet. Some of you, I saw some people nod like, oh, I remember something similar to this in grade 11. And I'll tell you at the end. For the last one, we have x plus 2 cubed. So here's my original graph. The plus 2 would move it 2 to the left, and then plus 1 at the end moves it up 1. And so if you did the yellow sheet first, that was your x cubed graph and everything that moved with it. Okay? You have those 3 key points. If you move those 3 key points and keep the shape the same, you'll be able to graph any x cubed graph which moves things left, right, up, and down. Second color we're going to do is the green one, the absolute value graph. The absolute value graph looks like this. Again, check. Did you have arrowheads on the end? The most important value on your absolute value graph is 0, 0, because that's where you sort of have the point where the bottom of the V-shaped graph is. You could label a whole bunch of other points easily on this graph, like 1, 1, 2, 2, 3, 3. There's lots of easy points you could graph. Now, if we turn over to the other side, we have to start deciding, how is this similar to the x cubed graphs? How do I know when to move left or right, up or down? For example, in this first one, I take my x plus 3 and I move it 3 to the left. How did I know that that plus 3 was to the left and not up 3? That's the first thing we have to start to realize, is looking for patterns. And again, can you see that that plus 3 is inside the absolute value? Anything that happens inside will move left and right. Anything that happens inside, or where the x was originally, affects the x values. Whereas in B, the plus 3 is now outside of the absolute value bars. It will move it up 3. And then C and D, we can start to combine things. I have a plus 1 inside the absolute value. That'll move 1 to the left. And then the minus 2 outside, that will move 2 down. And the last one, a minus 2 inside moves it 2 to the right, and plus 1 moves it 1 up. Be kind of nice if you could do that on your notes. Just draw your original and just take your finger and move it to where it needs to be instead of having to redraw it. Yes. Graph number 3, the pink one, the square root of x. The square root of x is interesting because it's the first one that has a restricted domain. When I say domain, those are our x values. Ranges are y values. It has a restricted domain because there are some things in math you're not allowed to do. Right? And one of them is you're not allowed to take the square root of a negative number. And so we can't take any square roots of negative numbers, so the smallest value you could put in is 0. And when you square root 0, you get 0. So we have 0, 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. And the shape of this graph looks like this. And the arrowhead is only on one side, because if you had the arrowhead going on the other side, it would say that you could keep going into the negatives, which is not true. So we've seen the absolute value and what moved it left and right. We've seen the cubic and what moved it left and right, up and down. Does the same pattern hold true with the square root? So if we go to the back side with the square root here, here's my original. What's that minus 2 going to do? Is it going to move it down 2 or to the right 2? It's going to move it to the right 2. Can you see that that minus 2 is inside the square root? Square root bar continued on. We would say that minus 2 is inside the function. It's where the x originally was, which is inside the square root. That will move it left and right. The x plus 2, again, it's inside the function. It will move it 2 to the left. For the third one, you have a plus 1 inside the function, moving it 1 to the left. The minus 2 is outside of the function. That will move it 2 down. And finally, we have a minus 2 inside the function, moves it 2 to the right. Plus 1 would move it 1 up. And we have our final graph. Each graph has the exact same shape as our original graph. It's just been moved. So before we get to our reciprocal one, which has a little bit more involved with the asymptotes, where have you seen this idea before? What does that graph look like? That's a parabola, right? Remember doing those? It has a vertex at 0, 0. You go over 1, over 1, up 3. You could do a table of values for it as well. Makes a nice U-shaped graph. Okay? In grade 11, you sometimes wrote it in vertex form. If I wrote something like this in vertex form, we called it vertex form because you could look at it and tell where the vertex was. Where's the vertex for this one? -3, 4. And it opened up because the a value was positive, and you knew you had to go over 1, over 1, up 3. And it had the same shape as the other one because it did that over 1, over 1, up 3. Now, if we think about what happens inside of a function, what happens outside of the function, can you see that the plus 3 is inside the function? That should move my graph, right? Right, here's my graph. That should move it 3 to the left, and then the plus 4 should move it up 4. And as you can see from my artistic skills, they match up perfectly. You can practically only see one parabola right now. So you've seen this before, but you never really talked about it as moving left, right, up, and down. But you've done that with parabolas. And the same idea holds true. You could even do it with lines, but lines is so, it's kind of interesting with lines. I'm sorry. It is really fascinating with lines because the basic line is y equals x. Okay? That has a slope of 1, y-intercept of 0. Okay? Oh, this is going to be fun. Okay. Is that 2 with the x, the way I've written it? So I should move it 2 to the left. Okay. I'm good with that. So there we go. 1, 2. 2 to the left. Perfect. Is this any different if I write it like this? Is that the same equation, or is that equation different? That's the same equation. I hope that's good. Okay? If I write it like that, it looks like the 2 is after the x. Then I should have moved it up 2. Okay. Sorry, I should have moved it up 2. 1, 2. Again, my artistic skills in drawing lines is so perfect that you can't tell the difference anymore. But it's the same thing with a line. So we don't ever do this with lines because y equals mx plus b is so much easier than graphing with lines. But it works with lines as well. And one of the things we're going to learn in our first unit is these rules work with every function. Doesn't matter if you start with x cubed, square root of x, absolute value of x, 1 over x. Later we'll do it with the log of x, the natural log of x, sine of x, cos of x, tan of x, any kind of graph you can imagine. You just have to know what the graph looks like to start with. So the key thing moving forward is you need to know what these graphs in the top left-hand corner of your first page look like. You need to know, I know that's my x cubed graph, these are the key points. And then I can move it from there. I know that this is my absolute value graph, and those are my key points. I know what my square root graph looks like, and some key points. And my rational graph looks like this. First of all, with your rational graph, you could plug in 1, and 1 over 1 is 1, so that would give you a point. You could plug in 2, and you would get 1 over 2, which is a half. That would give you another point. If you tried to plug in 0, 1 over 0 is not allowed. Another thing in mathematics that you're not allowed to do. You're not allowed to take the square root of a negative, and you're not allowed to divide by 0. Okay? Here's a picture of someone who tried to divide by 0 at their house, and it's, yeah, don't do that. It's just disastrous. So what happens with 0 being not possible, that shows up on our graph as an asymptote. We draw our asymptotes always with a dotted line. I like to use a red pen for an asymptote. So if you have a red pen, draw your asymptotes in red pen. That would be great. Now, if you kept going, you'd get 1/3, and then 1/4, and then 1/5, and then 1/6, and then 1/7. It will never go below 0. And so in this graph, you also have a horizontal asymptote at y equals 0. Vertical lines, the equation of a vertical line is always x equals. The equation of a horizontal line is always y equals. Do you know why that is? If I pick any point on this vertical line, I could pick this point right here. Here, I don't want this to show up late, so I'll make it -3, 0. Nope, sorry, I labeled it terribly. Scribble that out. So this would be 0, 3. This one would be 0, -2. This one would be 0, -4. What do we notice always? The x-coordinate is always 0. No matter which point I pick on that vertical line, the x-coordinate is always 0. And that's why the equation of that line is x equals 0. Same thing for this horizontal line. You pick any point on here, your y-coordinate will always be 0. And that's why we write the equation of that line, y equals 0. Now, if you plugged in some negative numbers like -1, you'd get -1, and the same thing happens over here. And we draw our graph towards the asymptote. I would have lost a half a mark on this question because I forgot an arrowhead on that one. They are very fussy on the grade 12 exam. Any small mistake has a deduction. They have 10 common errors that students make that they list on the exam. And if you make it once, you lose that error mark. Okay? Arrowheads is one of them. Here's another, okay, I'm going to just take this away for a second. Here's another common mistake. Okay, started off the same. Whew, got a little excited because you're almost done the question. What happened is my graph, which is supposed to go towards my asymptote, started to go away. Half a mark deduction, asymptote error. So when you have an asymptote, what an asymptote means is your graph gets closer and closer to it, but never touches it. So there's our rational graph. Do the same rules hold true with a rational graph? Yes. But it's a little bit harder to see what's inside a function and what's outside of a function with the rational graph. Again, if you think about where the x is, that's considered inside the function. In this first one, I have 1 over x plus 1. That plus 1 is outside of the function. That will move it up 1, and your graph will end there. The key points you need to know for your rational graph are your asymptotes and only these 2 points. Once you've got your asymptotes and those 2 points, you just need to draw your graph towards the asymptotes. Second one, this plus 2 is down where the x was in the denominator. This will move it left and right. So I'll have my graph starting there, x plus 2, 2 to the left. Third one, the minus 1 is where the x is. That'll move 1 to the right. Plus 2 will move up 2. So when graphing rational graphs, you will probably start with your asymptotes because they're really easy to move left and right and up and down. Draw them first. Then you could find these 2 key points and draw your graph towards the asymptotes. Finally, the last one here, we have x plus 3 moves 3 to the left. Minus 1 would move 1 down. And again, the shape of the graph stays the same. All that changes is where it's moved to. Left, right, up, and down. Now, a few things about domain and range, because the notation for domain and range is important. For these rational graphs, remember that domain is your x values, range is your y values. Now, for D, and I'll do domain and range for D on all of them, okay? For D, the domain, the x values, it's everything except x can't be -3 because we have an asymptote there. So the most simple way to show the domain is that x can't equal -3. Sometimes in textbooks you will see, oops, that's not a negative, that's a comma. X can't equal -3, and then after it'll say x can be everything else. That's okay, but not necessary. It is enough just to say x can't be -3. That is probably the most simple way to show the domain. But there are different forms of the domain. Do you remember doing interval notation for range, domain and range? So if you would do interval notation for this one, interval notation goes from left to right. What's the farthest to the left? Well, it starts at negative infinity, and it goes until it gets to 3, but 3 is not included. So we put a round bracket for a value that's not included. And then it starts again at 3 and goes all the way to infinity. When you have two different intervals, they're joined with a union sign in between, which means or. It's from negative infinity to negative 3, and then from negative 3 to positive infinity. So in this situation, I would probably recommend that as the most simple way to write it. But if you were given a multiple choice question and they had more information, I just need you to know that that's okay. Or if they gave you interval notation, to understand what it means. Same thing on this one. If we did the range, the simplest way to do the range on this one is to notice there's an asymptote at negative 1. So I would just write y can't equal negative 1. We'll do a domain and range from each of the other ones as well, just to see some of the differences and to remind us of some of the notation. So here's our square root. If we did part D of our square root, if I wanted to find the domain of this one, those are my x values. I can't take the square root of a negative number. The smallest x value that I ever have is positive 2. So I could write my domain as x is bigger than or equal to 2. That would be fine. Or I could write that in interval notation, which would go from 2 to infinity. Notice that this time in interval notation, I used a square bracket. A square bracket in interval notation means that value can be included. A round bracket, when you have an asymptote or with infinity, means that value isn't included. If I did my range for this one, same kind of idea. My smallest y value is 1. Y is bigger than or equal to 1. Or I could write that as 1 to infinity with a square bracket. Going back to our absolute value functions. Again, looking just at part D. If I did the domain, I can see from my graph that it goes forever to the left and forever to the right. But the domain is really asking, is there anything not allowed? Right? With square roots, I couldn't take a square root of a negative. With rational graphs, I can't divide by 0. But there's no restrictions here. I don't have square roots. I'm not dividing. Every single x value is possible. So probably the most common way to write is x belongs to the element of the reals, xer. That means everything. That's in set notation. In interval notation, you could write from negative infinity to infinity. That means everything. The range of this one, though, it does have a smallest value. The smallest value is 1. So you could write y is greater than or equal to 1. Interval notation, that would be from 1 to infinity. And finally, our x cubed graph. You can cube any number, so the domain is everything. This graph goes up forever and down forever. So the range is everything. picked all boring graphs. Let's go back. One more thing to look at. What was the last one here in D? X cubed plus 2? X cubed minus 2? Okay. So you took your x cubed graph and you moved it down to, giving you a point here, and a point here. And this was the graph. Now, one of the things you were asked to find was an x-intercept or a 0. And I wanted to pick this graph because it doesn't turn out nice on your graph. It's not a nice point. Whereas all the other ones, sometimes you could just look at your graph and see the point easily. So a review. How do we find x-intercepts and y-intercepts? You can find an x-intercept because you know that the y-coordinate will be 0. Algebraically, you can find an x-intercept by plugging in 0 for y. Now, if I plug in 0 for y into the equation, I get 0 equals x cubed minus 2. If I want to find what my x-intercept is, I have to use my algebra skills to get x by itself. How would I do that in this case? I could add 2 to both sides. How do you get rid of a cube? You cube root. So x is equal to the cube root of 2. You could type that into your calculator to get a decimal, or if you wanted to leave it exact, you could label it as the cube root of 2 comma 0. So that's just a little review for solving x-intercepts and y-intercepts. You've done that a lot in grade 10 and grade 11, and you do it a lot again in grade 12. Finding x-intercepts and y-intercepts is really important. Sometimes you can just see it easily from the graph. Other times you have to do it algebraically, like in this case. So tomorrow's class,